Hello students, in this session we will do the chapter of work, energy and power. So we need around like 4 sessions to complete this chapter. So the concepts that we will see in this chapter will be like the physical and intuitive understanding behind the term work. Okay, so how should you actually understand work in terms of physics? That will be done, and then we will see the formulas related to work. Got it? So that will be simple, and then we will do like a new kind of multiplication, vector multiplication. In the previous chapters we might have done different stuff that are related to vectors. For example, resolution of vectors would have been done same way we did like addition, subtraction of vectors, and then we did also do vectors in three-dimensional stuff and all those stuff, right? So you should be clear with all those topics that we have already learned. So in this session we will see a new kind of multiplication between two vectors. Fine. So there are actually two different ways by which we could actually do the multiplication. One is like the dot product and the other one is like the cross product. Okay, so in this chapter we will do like dot product, in the next chapter we will do like cross product. Fine. So those two things are kind of different multiplication that we could actually do in the vectors. Fine. So we will do that stuff. Then we will see like how to understand like kinetic energy and those stuff. That derivation part will also be done, and then we'll see like potential energy, and then the vertically hanging pendulum and how does it actually the energy changes with respect to its position will also be done. Finally we will do like collision. Got it? So that those are something that we will see in this chapter. So in this first session we will do like three important concepts. First one is like the work, the basic understanding, and then we will see like the dot product. Okay, so what is the mathematical background towards the dot product which we need to know, that will be done. And then we will see and then we will see something like derivation of the kinetic energy. Okay, so these three stuff will be done in this session. Fine. Now let's jump into the chapter work, energy and power. Got it? So work and energy, even if I use these two terms interchangeably, it simply means these two are actually the same thing. Okay, so it doesn't matter whether I tell you work or energy, both those terms actually signifies the same understanding and logic. Okay, if you consider power actually means what was the energy consumed in unit time. Okay, so generally in SI units we'll consider the unit time to be like second, therefore the energy consumed in unit time or unit second will be called as power. Fine. So we will see power in the upcoming sessions. As if now we will see what is meant by work. So work, energy, both those terms actually signifies the same understanding. Fine. So that's what you need to know. So to get an understanding for the work, what we are going to do is I'm just going to do an experiment over here. Got it? So I'll take a mass or a ball or an object. Okay, so I'm having an object in my hand. What I'm going to do is I'm just going to give certain amount of work to it, which means I'm just going to throw it upwards by giving work to the ball from my hand. Okay, so I'm the one who is giving the work and the work is getting received by the object. Okay, so that's how it's going to be. Therefore once the object receives the work, what will happen to the object? It will start moving upwards with certain velocity. Okay, so that will be the initial velocity with which I throw it upwards. Fine. So then after some time it will reach certain height. Okay, so when it has reached the certain height, I know the velocity will keep on decreasing and then it will reach certain height. So after reaching that particular height, what will happen? The velocity will become zero. Therefore, it will change the direction of the motion and it will start falling downwards. Fine. So and it will start falling downwards and then it will reach the earth with the same amount of velocity that I gave to the object. Fine. If there wasn't any air resistance in between. If there was air resistance, obviously some part of the energy from the ball would have transferred to the surrounding air molecules and other stuff. That would have happened. But in this situation, let's simplify it. Okay, let's idealize it. So here with whatever velocity I threw it upwards, it came back with the same velocity. From kinematic equation, we obviously know. So with whatever velocity I threw it upwards, it came back with the same velocity, means whatever energy that I gave to the ball, I just got it backwards. The direction might have changed, but the point is it still had the same amount of velocity into it. Okay, same speed, magnitude of velocity into it, right? Therefore the energy is pretty obvious, it is conserved in the situation. Fine. So whatever situation that you consider in upcoming different experiments that we will do, and then in different scenarios, energy will always be conserved. Fine. So it might have transferred into other forms like heat energy or else the light energy, that could have happened. But if you sum up all those energy will always be conserved. Fine. So that's the intuition with which I'm going to build this concept. Fine. So energy will always be conserved. It will not be created neither be destroyed. Okay, so it will always be conserved, fine. So this is something that we might have already known from our lower grades itself, fine. So here it is pretty obvious. I'm just going to throw it upwards. So it has moved upwards to a certain distance d. Yes. Okay, so this will be the distance displacement that it has traveled, fine. So here I'm just going to solve everything in vectorially, therefore I'll consider displacement. Got it? You should be clear. So here if I just consider how is actually the force and the displacement is acting. Force is acting downwards and the displacement is actually acting upwards, right? So d, the direction of motion of the ball is upwards. The gravitational, see, I have given to the ball force in upward direction and it more amount of energy got stored. Because of that, it started moving upwards against the gravitational field. Okay, so by considering the gravitational field, I'll find out how far I have given energy to it. Got it? So here the displacement was upwards, acceleration due to, force due to gravity was actually downwards. Got it? So these two things are opposite to each other. Therefore, the angle between them will obviously be like 180 degree. So here they are in alignment to each other. Okay, so D and F are in aligned. Same way, if you consider the direction, then they are actually anti-parallel to each other, fine. So one is like opposite to the, exactly opposite to that of the other. If this was the case, then we are moving against the force field. It is pretty obvious we are moving against the force field. Therefore the energy in terms of velocity got reduced and it got stored in that force field. Okay, so once it has reached that its topmost point, what would happen to it? It will just fall exactly downwards, right? Got it? So that will be the case where the energy will be released. Okay, so in the initial situation, when the force due to gravity and the displacement was opposite to each other, the energy got stored and the velocity got decreased. Okay, once it has reached the maximum position, when it was about to fall down, what happened was whatever energy that got stored, it got released, and when it reached the same position, the same amount of energy was converted to the velocity. Okay, which means in that situation the energy was in the form of kinetic energy. Okay, so whenever you have translation into it, I'll call that energy to be like kinetic energy, which we will do at the end of the session, fine. So you should be clear with this understanding that I've told you over here. Got it? If you consider the situation when the ball is about to fall down, obviously the displacement d, got it? So the displacement d and the force field both will be along the same alignment. So in this situation the energy will be released, right? So when D and the F are anti-parallel to each other, in that situation, the energy will be stored into it. Same way, when F and D are parallel to each other, in that situation, the energy will obviously be released. Okay, so these are two different situations that we need to know. Got it? So then what we will do is, so let us consider another one situation. So here when we have found out what will happen when they are parallel and anti-parallel. Okay, so the next obvious case is what will happen when both those components are perpendicular to each other. Got it? So let me put it this way. I'm just going to throw a ball from the earth's surface and it has reached the maximum height. Okay, so that stuff is done. What I'm going to do is I'm just going to hold the ball in my hand. Okay, I caught the ball on top of the tower, something like that. I'm just going to hold it on my hand, fine. Then what I'm going to do is I'm just going to move this ball perpendicular to the direction of the force field. Okay, which means horizontal in this situation. Okay, so now I'm just going to move this stuff horizontally to certain displacement d. Okay, so what I'm going to do now is I'm just going to catch the ball and then I'm just going to do certain distance d horizontally and I'm going to drop it. Okay, I'm not going to drop it at the point where it has reached. Instead, what I did is I just moved it certain distance horizontally and then I dropped it. If that was the case, it should be pretty obvious because of the horizontal motion of the ball, there wouldn't be any extra energy stored into the ball, right? So even if I drop from this position and still if I drop at certain different position, and what I did was I just moved horizontally in both those two different positions, I'll end up having the same velocity with which it is going to reach the ground. Got it? So here this horizontal displacement doesn't constitute to any energy storage in that particular ball. Okay, if I have moved vertically upwards, in that situation energy had stored into the ball and I ended up getting extra velocity into it. But I did move here horizontally to the direction of the force field, which means perpendicular to the direction of the force field. Okay, so if that was the case, then no energy, extra energy will be stored into it, right? So when you have the velocity is something like this. When you have the direction of the motion something like this perpendicular to the direction of the force field, okay, if that was the case, then obviously the energy will not be stored into the ball because of that horizontal motion. Okay, therefore here the energy wasn't stored, right? Because of this motion the energy wasn't stored. So from this it should be pretty clear, work will be involved only when you move in alignment to the force field. Okay, so when you are going to move perpendicular to the force field, if that was the case, then obviously work will neither be stored nor be released. Okay, so that is not going to happen. Obviously only when you have in alignment F and D component, in that situation we will have something involvement of work into it, right? So let's now what we will do is, now let's find out what are all the parameters that are needed to find out what was the amount of work that has stored into it. Okay, so now I just have to fix the parameters that is needed over here. Fine. So from this experiment it should be pretty obvious, work should be created because work has been stored or released because of the force and then the displacement. Okay, so these two parameters are obviously involved. Okay, so let me give you a simple situation. If I'm just going to move double the amount of this height, then obviously when it is going to reach the earth, it will come with greater velocity than that of this situation. Fine. So obviously the work has doubled in that situation. Got it? If I give like double the amount of work to that particular wall, then obviously it has reached the double the distance. Okay, got it, in the same amount of force field F. Okay, so that was the situation. Then it should be pretty obvious, F and then the D, these two parameters are involved. Then another one parameter that is left over here is actually the time. Okay, so time will not be involved because let me give you a consideration. I'm just going to throw a ball and it reached the maximum height, and what I did is I'm just going to hold that ball in my hand for a few more extra minutes. Okay, so even if I just hold it for hours or minutes, whatever it is not going to gain extra work. Same when I'm about to release it, it will reach the ground with the same velocity. Then it is pretty obvious it doesn't depend on the time, right? Holding that ball for 1 hour in your hand doesn't constitute extra energy storage in that particular ball. Okay, so only the parameter that is involving over here is the displacement and then the force. Same way the parameter time doesn't come into picture. Okay, even in that situation, the horizontal, I mean the perpendicular displacement wasn't responsible for the storage of energy. Okay, so now, so next what I will do is I'll just figure out a way to remove that perpendicular component. Okay, so as if now we have found there are like two components that are involved for the work. Those two components are like the force and then the displacement. Got it? So F and then the T. So these two components will be responsible for the energy storage. Got it? So F and then the D for the production of, for the involvement of work, F and then the D will be needed. Got it? Fine. So if I'm about to multiply these two parameters, obviously these two stuff are actually vectors. In one situation, those two were along the same line, were parallel, and in another one situation, those two were anti-parallel towards each other, right? So first let me consider as the third situation where F and then the D were parallel to each other. If that was the case, F is in the negative direction, same way displacement was also in the negative direction. If I do the multiplication of F and D, I'll end up getting the positive answer. Okay, if work was positive, what will happen to the work? Energy will be released. Got it? So when F and then the D is going to be positive, then in that situation the velocity will keep on increasing, which means while looking at it, it will become clear that the energy is getting released in the form of velocity or translation. Got it? So when work is positive, energy is released. Okay, this should be obvious. In what form actually it is getting released is in the form of translation or in the form of velocity, whatever it is. Okay, in the form of velocity. Got it? So here in this case, F vector F and then the D vector are actually parallel to each other. Got it? Plus and plus becomes minus, or negative and negative becomes positive. I mean, plus and plus still gives you the positive direction. Same way, negative and negative still gives you the positive direction. Got it? So F and D vector are parallel. Got it? Then you have got work done to be negative. So if you consider the first situation where F and then the D are opposite to each other, this was the case where work was negative. Got it. So here work is negative, which means energy is stored in the situation, because as the ball was moving upwards, the velocity got released and it got stored into that ball because of that force field. Okay. So once it has reached the maximum position, the energy will be released in the other direction. Okay. So because of that involvement of force field, the energy got stored into that ball. Okay. So that will happen when both those F and D are opposite to each other. So here the energy is released. I mean, the energy is stored. Fine. So here the energy got stored. Vector F and vector D are anti-parallel to each other. Are anti-parallel to each other. Okay. So this was the simplistic situation where force and then the displacement were in aligned to each other. if if it was like other way around, if it was like perpendicular to each other, then it is obvious that situation work will be zero. But if you have a certain inclination, the force was acting on that object, if that was the case, then I'll have to remove this perpendicular component and I'll have to consider only the in aligned component. Okay, so to do that, I've just taken a simple experiment over here. Okay, so while understanding this stuff, we will get into the picture of dot product, which is called as scalar product. Okay, so you have another name to it, which is called a scalar product. I'll tell you the reason why we call it a scalar product. Okay, so here you have got an object that is going to travel a distance d, distance or displacement d in this case. Fine. So even if I tell you distance, you should be clear, I'm just mentioning displacement over here. Got it? So you are having an object and then I'm going to give a force at certain inclination to that particular object. Fine. So because of this force, it's not going to move in this direction, in the same direction of the force. It is going to move at certain inclination to the direction of the force. Fine. So one component of this force will be responsible for the work and the other component will be perpendicular to it, which will not be responsible for the work. Fine. So now what I have to do is I'll have to remove that perpendicular component from this entire force F. Okay, so to remove that one, what I'll do, I'll have to do the resolution of vectors and I'll end up getting the component that is in alignment with the displacement d in this situation. Got it? Fine. So to get this, to do the resolution of vectors, what I need to do is I'll have to get the theta between them. Fine. So whenever they give you like two components and they're asking us to find the theta between them, what we have to do is we'll have to match the tail of those two vectors. One vector is like vector f and the other one will be like the vector d. Okay, so if I do match these two tails, and I'll end up getting the theta between them. Got it? So this is how I'll have to match, right? So this will be the vector d and this is my force f. Therefore the theta between f and d will be this component. Fine. So I'm just ready to do the vector resolution over here. So if I do the vector resolution, you will have two components split, horizontal and perpendicular. So this will be my theta because this will be the point where those two tails met. Okay, so it should be clear. So this component will be like f cosine theta and this component will be like f sine theta. Got it? Fine. So the component that is in alignment to the displacement will be this f cosine theta, and it is pretty obvious these two f cosine theta and d are parallel to each other, which means energy will be released in the form of velocity in this case. Got it? Because these two components are parallel to each other, therefore obviously these two sum up to the positive. If work done was positive, then obviously the energy would have been released. Got it? Therefore here, to get the force, the component that I need to consider will be like f. I mean, let me put it this way: modulus of vector f cosine theta, modulus of vector f cosine theta, and then you'll have like modulus of vector d. Okay, so those two components will be involved, right? So now what I did is, instead of considering this fd straight away, I just took the cosine component between them. Fine. So if they were in aligned to each other, in that situation theta will be 0. Therefore cosine 0 will give you the answer to be like 1. So that wouldn't be a problem. So that was when you have those two components to be in aligned. When you get that component at certain inclination, in that situation I'll just have to consider only the cosine component. Sine component will not be considered because that will be perpendicular to the direction of the motion. Okay, so that stuff will not be considered. Okay, so when you consider like cosine theta, this is a kind of special product that we do using the vectors. Okay, so that product is called as dot product. Okay, so the notation that I'm going to use is like the dot. as the name suggests, you will have like vector F dot vector D. Okay, so here I have done the dot product, and the unit for the work will be like, obviously it is simple, right? Newton and then meter, or else I'll be able to call this one as joule. Okay, so you should know these units. So whenever they are giving you the energy or work, they'll represent it in terms of joules. Fine. So here this dot product is, this kind of product is called as dot product or scalar product. Got it? Fine. So you should be clear with this stuff. Now I'm just done with scalar product when they have given you the angle between them. Okay, in generalized situation, they'll just give you those two vectors, they wouldn't give you the theta between them. If that was the case, then how should I actually do the product? So that's what we are going to see next. Fine. So to do the scalar product, when you do not know the theta between them, only thing that they have given us over there is the two vectors. Okay, in terms of I cap, j cap, and k cap, they're given you in that fashion. How should I actually do the product? That's what we are going to see next. So here, to do the scalar product, what we have taken over here is actually there are like two components. One is like vector A, which is equal to 5 I cap. Okay, and I have taken the next vector, which is like vector B, that will be equal to 6 I cap. Okay, so those two components are considered. The angle between them is obviously 0 degree, right? Because they are parallel and they are in aligned. Okay, therefore theta will be like 0 degree. In the first situation, theta was equal to 0 degree. Got it? If I need to do A dot B in the normal fashion, how would I actually do it? Is like modulus of vector A, modulus of vector B, and then the cosine theta between them, right? So you will have something like this: modulus of vector A, and then modulus of vector B, and then the cosine 0 degree. Got it? So here obviously cosine 0 degree equates to 1. So I'll just have to consider these two modulus, which means the magnitude, and multiply it with it. So you'll have like something like this: 5 into 6, so 6 5s are 30. So that will be my answer. So this is how generally I do the scalar product. Fine. But in every single situation, it will become hard to find the theta between them. This was a simple case, therefore it was easy for us to find the theta. But if they're given you randomly two different vectors, that will become obviously hard. Okay, so if that was the situation, then what I'll do is I'll just multiply the same component with each other, just like a normal multiplication, including the negative sign. Okay, so let me do it in this fashion. So generally when they give you these two vectors, what you do is you just write the first vector 5 I cap and then dot 6 I cap. Okay, just do the multiplication straight away, you'll end up getting the answer of the same component. Okay, so 5 6 into 5, that will give you like 30. Fine. Okay, so it is not necessary that you find the theta and then you do the multiplication. That's not needed. If those two components were just the same thing, just do the multiplication, you'll end up getting the answer. That's it, finished. Okay, so next what we will do is we will see if they are anti-parallel to each other. Obviously you should get that extra negative sign, right? So if it was like anti-parallel to each other, then it will be like theta will be equal to 180 degree. Got it? So for that, you'll have like modulus of vector A, and then you'll have like modulus of vector B cosine 180 degree, right? So cosine 180 degree will be like negative 1. I mean, cosine 180 degree, so that will give you like negative 1. Got it? So if I do the multiplication, modulus and modulus, that becomes like positive value. Therefore, you'll have like 6 into 5 into negative 1. That will give you obviously negative 30. Next, let me do the dot product by using the normal way. Okay, which means I'll just take it this way: minus 5 I cap dot minus 5 I cap dot 6 I cap. Okay, just multiply the same component, you'll end up getting the answer, right? So I'll have to consider the negative sign, therefore you'll get the answer straight away. That's going to be like negative 30. Okay, so it should be obvious that when you do the dot product, it doesn't matter to find the theta between them. Got it? Just do the multiplication of the same component, you'll end up getting the answer. So it should be clear. When you get the answer to be like positive, in that situation, the energy will be like released, work will be like released. Same way, If the answer was like negative, in that situation, the energy got stored into that particular object because of that force field. Okay, fine. It should be clear. Then what will obviously be the case for the cosine 90 degree? Obviously, the cosine 90 degree, when two components are perpendicular to each other, you'll have like different components involved, right? When you got like same components involved, just do the multiplication, you'll get the answer. Obviously, when you have like different components involved, the angle between them will be like 0. Got it? Cosine 90 degree will be like 0. So in this situation, if I do the dot product between them, what will I end up get? What will I end up getting is actually vector A, modulus of vector A, modulus of vector B, cosine 90 degree, that's going to be 0. Therefore, whatever the magnitude that you get, you'll end up multiplying it by 0. Therefore, it will be like 0. So it should be pretty obvious that perpendicular moment with respect to the force wasn't responsible for the energy storage or energy release. Therefore, it is pretty obvious only the component that is in aligned to the direction should be considered. If it was like perpendicular, then it shouldn't be considered, right? So here it is clear that modulus of vector A dot vector B is 0 if those two components were perpendicular to each other, right? So I will be able to generalize here in the situation. Here you have got like I cap dot j cap, right? So I'm just going to do the dot product between I cap and then the j cap. These two components are perpendicular to it, which means then angle will be like 90 degree, cosine 90 degree will be like 0. Therefore, I dot j, j dot k, k dot I, or negative k dot I, whatever it is, you will still end up getting the answer to be 0. Fine. So when you have like different components involved, you should be clear. The answer will be like 0, right? So here, because they will be perpendicular to each other, so these component will multiply to 0. Got it? So now I'm ready to do the dot product for a real three-dimensional vector. Fine. So in the above situation, I did it for like only one dimensional and I just involve like two-dimensional stuff. Okay, which means I and j, something of that sort. Now here I'm just going to consider a really huge vector, which means like 5 I cap, 3 j cap, 2 k cap, a fully blown vector here over here, and then same way you do have like here you have like vector over here, right? So I'm just going to do the multiplication of vector A dot vector B. That's what I'm going to do it over here. So you will have 5 I cap plus 3 j cap plus 2 k cap. Got it? So I'm going to do dot product of this vector with the vector B. That will be like 3 I cap plus 7 j cap. Got it? If I do the dot product, you will have I'll have to multiply same component with the same one, right? So I'll multiply 5 with the 3. Same way I'll do the multiplication of 3 with the 7. And then you do not have k cap into it, k component into it. Therefore, I'll have to obviously consider that to be like 0 k cap. You do not have any values along the z direction, right? So that will be considered to be 0. So in this situation, you'll have like 2 times 0. That will again give you the 0, right? So 2 times 0 will again give you the 0. Got it? If I do the multiplication, I'll get the answer. So if I do the multiplication, you'll have like 5 into 3. That's going to be like 15. Yeah, 15. So the answer here is positive, which means the energy got released because of the involvement of x direction on the I component. Okay. Then you have got the next component to be like 3 into 7. Even in that case, the answer was like positive. Therefore, here also the energy got released. Got it? So if I do add those two stuff, I'll end up getting the answer, which will be like 21 plus 15. That's going to be like 36, right? Yeah. So the answer here is 36. Yeah, so now I have done the dot product of fully blown vectors, vector A and then the vector B, right? You should be clear how I have did actually the dot product, right? You shouldn't have any doubt. So here in dot product, when you get the answer to be positive, in case of work, when you get the answer to be positive, you should be clear the energy got released. Okay, if the answer was like negative, it should be obvious that the energy got stored because of that force field into that particular object, right? It should be clear. Fine. So when you do the multiplication, something like of this sort, one component might give you the answer to be positive, another component might give you the answer to be negative. Okay, once you do the addition of those two stuff, you could either get the answer to be positive or negative. Same logic will be applicable even in that situation for the final one, which is if it was like positive, then the energy got released. If it was like negative, then the energy got stored in that into that particular object. That's what you need to know, right? Got it? So this is what is meant by dot product that you need to know. Fine. By this time, you should be clear by the definition of work, what you need to know regarding work in terms of physics should be clear. So the formula for the work is like force times the displacement. Time will not be the parameter that will get involved. So just leave that time. Got it? So to get the work, we are going to introduce a new kind of multiplication vector which is called as dot product. So in that multiplication, what I'm going to do is I'm just going to throw away that perpendicular component, which will be the sine component. I'll just consider only the cosine component. Fine. So this is what you need to know regarding the dot product or scalar product. Fine. So next we are into the last part of this session where we will do the derivation part for the kinetic energy, right? So to get the formula for the kinetic energy, I'll once again consider a simple experiment, fine, same experiment that we have already considered. And what I'll do is, I'll just use the same work done formula and I'll end up getting the value of work in terms of velocity, fine. So let me do the experiment, you'll get it. So you're having an object and then I'm going to give a force at certain, here in the situation horizontally, fine. So it is also going to move horizontally to a distance d. So the force has been given to this object till this distance, okay. So because of that force, what has happened to that particular object is it has gained certain velocity, fine. So obviously f and d are parallel to each other, therefore velocity in a work would have been released because they are parallel to each other, right? It is not moving against the force field, it is moving parallel to that of the force field, okay. So here in this situation, it is pretty clear and obvious the energy is getting released in terms of velocity, fine. So what I need to know is, if I just only know the velocity and mass of this particular object, I should get what was the amount of force that was given to this object and what was the distance to that particular distance, okay. If I do the multiplication, I'll end up getting the work. I do not know what was the force that was given to that object. I do not know how far it has traveled because of that force, fine. Only thing is, I just know the output, which is like mass and then the velocity. By using these two terms, I should know how should be the multiplication of force and displacement. That's what I need to get over here, right? You should get this idea. So now to get that stuff, first let me consider the force and then the displacement that it has moved. Obviously in this situation, it is just going to move unidirectionally along the x component, fine. Therefore here it is pretty obvious the small element that I'm going to consider will be like dx, which will be along the x direction. Got it? Fine. So to get the work done, obviously work is the dot product between the f and then the displacement. Therefore here you will have like vector f dot vector d. Got it? But over here it should be clear. I'm just going to move along only x direction. Therefore dw, and same way it should be clear. Here I'm just going to consider the small amount of force, small amount of work. Then what will I do is I'll just integrate it to get the complete work, fine. I'm going to do an integration over here. That logic should be clear. Therefore here if I have to do the integration, it will be like vector f dot dx. Obviously dx will be along the x direction, so this component is obviously positive, therefore dx I cap. That's how it's going to be, right? This term should be clear. So to get the work from it, what I have to do is I'll have to integrate it, right? So to do the integration, I'll have to plug in the limits. So you'll get something like this, vector f dot dx vector, or else you could put it like dx I cap. Both those just represents you are considering the direction, fine. So now I'll have to do the integration. If I have to do the integration, it will be from the initial position, which will be like 0, to the final position, which will be the d. Got it? It will be like 0 to d, and then if I do the integration, f will be like constant. You'll end up getting the first this result itself, which is like f times t, right? What I need to know, what I need to get is actually the answer in terms of velocity. Therefore I'm just going to apply in terms of velocity itself. For that I'll have to change this displacement in terms of dv variable. Same way force will also be changed accordingly. Got it? So here if I plug in like 0 to the final displacement d, I'll end up getting the same, the first initial step. So that shouldn't be the case. I'll have to get the answer in terms of velocity. Therefore initially the velocity was 0, it was at rest. Finally it got certain velocity because of the energy input into it. Okay, so whatever energy that I have inputted into that particular object, same amount of, accordingly you'll have like velocity, accordingly you'll have proportionate velocity into it, right? Therefore by looking at the velocity, I'll have to tell what was the energy that I gave into it. That's what I'm supposed to find over here. Therefore, here you will have the initial velocity to be 0 and the final velocity will be like the v. Got it? Therefore, I'll have to change this dx variable into dv. That is when I'll be able to substitute the upper limit minus the lower limit. Okay. So next step will be such that I'll have to remove this dot product from it and then I'll make it into a scalar component. Okay. So if I have to get that one into a scalar component, I'll just have to do the dot product between those two stuff. It is pretty obvious. If I do the dot product, you'll have like 0 to v and then modulus of vector f is the f and then dx I cap will give you like dx. What was the angle between them? F and then the dx were parallel to each other. Therefore, the angle was like 0 degree. So cosine, you'll end up having like cosine 0 degree. So this will amount to 1. Okay. Now what I did is I just removed those vectors from it. Now I'm just worried only about the magnitude in the situation. Initially, I have got like vectors into it because of the dot product. So once you do the dot product, you end up getting once you do the dot product, you end up getting the scalar. That's why it is called a scalar product. Okay. In that situation, plus and minus represents storage and then the releasing of energy. But here it is pretty obvious those two stuff are actually aligned to each other and parallel. Therefore, energy would have released. The final answer will be like positive. It should be clear. Therefore, cosine 0 degree was equal to 1. Now I just have removed vectors from it. Now I'm just worried only about the scalar component, fine, which is like f and then the dx. Magnitude is something that I need to find over here, right? So to get this f in terms of v and then the dv, what I'm going to do is I'm just going to use that formula which is like f which is equal to ma. Okay, I'm just going to take this formula straight away and then I'll just do some rearrangement into it and I'll get v into that particular formula, right? Let me do that one. So here you have got f which is equal to ma. So you do not want to worry about the vector vector f is equal to m times vector a because it is pretty obvious this direction of motion is unidirectional. It is along the positive x-axis. By using that stuff, I have already removed the vectors into it and then I just removed the dot product from it. It was like cosine 0 degree that was equal to 1. Okay, so now I'm just worried only about the magnitude of force that is actually acting on that particular object. Okay, so f which was equal to ma. Even if you plug in like vector sign, that is not going to be of any use to us. Therefore, f will be equal to ma and then so now I'm just going to rearrange this stuff which will be like dv divided by dt. Okay, so that's how it is going to be, right? M instead of acceleration a, you'll have like change in velocity divided by the time interval. Got it? Now let me do a rearrangement into it. I'll multiply it by dx and then I'll divide it by dx to this particular term. Okay, so next what I'm going to do is I'm just going to consider the same term as usual, which is like dv divided by dt. I'll multiply it with dx. Okay, and then I'll divide it by dx. Fine. So if this was the case, now I'll be able to consider this term, okay, as the velocity v, right? So this term dx by dt is nothing but the velocity in that particular direction. Fine. So this is unidirectional. There wouldn't be any dy component or dz component. Okay. I've already set the experiment in a very simpler fashion. Okay, even if you end up involving different components, you will finally get the same answer into it, right? So if it is valid along the one direction, then obviously even if you take any arbitrary direction, still it will be valid in that particular direction. So that's the idea and the thinking behind it. Okay, so here to simplify it, I just consider it to be along the x direction. Therefore, dx by dt will give you the velocity in that particular direction. So then you are just left with dv divided by dx. Therefore, now I have just rearranged this ma formula into a different kind of differential equation, which is like m, and then dx by dt will give you like velocity v, and then you have got like dv divided by dx. Okay, so this is the arrangement that is needed for me. Now I'll just plug this f into the above equation that I've got over here. Integral equation, which is like integral of 0 to v f dx. So instead of f, I'll substitute mv dv by dx. Okay, so here you have got integral of 0 to v and then f dx, right? So for f, I'll substitute m v dv divided by dx. Okay, and then you have got dx. Okay, so that's what you have got over there, right? Now I'm just done with the dx. Those two terms will get cancelled out. Dx will get cancelled out. Only parameter that is left over here is mv dv. So now I'm just ready to do the integration because it is pretty clear that you have got the velocity v, that was the variable that was needed. Same way dv was the differential element. Now I'm ready to do the integration with respect to 0 to v. Now I have changed that limit, that parameter from dx to dv. Okay, and the limit was also favorable in the situation, which is like v. Therefore now I could do the integration, right? So once I do the integration, you'll have like m, which will factor out from the differential integral, because that term is actually a constant. Then you have got like v dv. If I do the integration of that stuff, you will have like v square divided by 2, and the limit will be from 0 to v. Got it? If I apply the limits, you will end up having half mv square. So that will be my answer, right? So m, okay, only part that will be left is the v square by 2, and the next one will be like 0. Therefore that term wouldn't come, right? So here the kinetic energy was actually equal to half mv square, right? So this is the formula that we might have already learned in our lower grade. So this will be the derivation for this particular formula. Okay, so only if we know the integration and differentiation, we'll be able to get this result, which is like half mv square, right? So from this formula, half mv square, what we actually found is we had an object that was under the influence of a force, and it did travel certain distance d in that force field. Okay, because of that force field, certain amount of energy got released from that particular body, which was equal to, which was translated in the form of velocity. Okay, so that is how when I finally looked at that particular object, there was velocity into it. I do not know what was the force, what was the displacement. Obviously, then I do not know what was the multiplication of those two terms. Then, which means I will not be able to get what was the work that was given into that particular object just by looking at the velocity and the motion of that particular object, right? So, to get that energy stored into that object, what I'll have to do is I'll have to just multiply. I'll just have to do the multiplication of mv square and half. I'll end up getting the kinetic energy. So that kinetic energy will give you the multiplication of those two terms, which will be the force field times the displacement, which I do not know, right? So just by looking at the final output, I'll be able to tell what was the work that was stored into that particular object, because I obviously know the mass of the object. Same way, I obviously know the velocity. With those two stuff, I'll be able to get the work that was actually given to that particular object which was released, right? Fine. So it should be clear, right? So the concept that we did see in this chapter were like the intuitive physics background behind the work and energy, right? Work and energy, both those terms are just the same thing, right? Then we did see the scalar product or the dot product between the force and the displacement, and what was the mathematical understanding that we need to know, right? So we did see a different kind of multiplication, which was like the scalar product. Finally, we saw kinetic energy, and how did we get to that answer, half mv square? We already know the kinetic energy was equal to half mv square from our lower grades. So this is the mathematical background that you need to know regarding the derivation of kinetic energy, right? So with this, the video gets completed. You should be clear with all those concepts that we have seen, right? Thank you. Bye.